Okay, so let's think about question B and C from homework 4, question 2. Um, so in part A, we consider two-stage least squares estimator. Now we are going to think about GMM estimator. So the setup is the same. We have two instruments. One is the regressor and the other is excluded instrument. And uh, the exogeneity condition is like this equals to 0. But as you know, we would like to rewrite epsilon as like say y minus beta 0 xi is 0. So we wanted to define a moment function gi as this, right? So the moment function is instrument times epsilon, but remember this is 2 by 1. This is a 2 by 1 vector. This is the moment function, and then the optimal weighting matrix. Remember, optimal weighting matrix W is omega inverse, where omega was the variance of gi beta 0, right? So when beta is the true value, the variance of the moment function is omega, and its inverse is the optimal weight matrix. In this case, because G is 2 by 1 vector, omega will be 2 by 2 covariance matrix. And especially, and as you know, when G, like when beta is beta 0, Gi beta 0 is Vi times variance epsilon, right? V epsilon, Vi times epsilon, right? And under the assumption that we assume in the question, we assumed homoscedasticity because we assumed, given that so this is the homoscedasticity assumption, and because we have this by the law of iterated expectations, we have variance of Vi V epsilon I is, right, it is this one, okay? So this kind of algebra is well known from the OLS variance, okay? So then therefore, hence, the optimal weighting matrix should be like things like this. But because the constant, because sigma square is a positive constant, it does not affect the minimization problem, GMM estimator. Thus, we can just simply drop this from the weighting matrix and estimate by. So you know how to estimate this. V prime will be estimated by the sample average. The V prime expectation will be estimated by the sample average of V prime, and then of course inverse should be taken here. this would be uh, our weighting matrix we are going to use. Additionally, in this question, I am asking you to use matrix notation. Uh, remember, remember, like VI is like 2 by 1, two by 1 vector. Suppose that is n by 2 matrix. So we have n observations of uh, V. So n observations of V, and each V is 2 by 1. So we can make an n by 2 matrix like this, and I will denote that as calligraphic, like capital thick, like V. And then you can easily see that this summation can be written as, by the way, the summation is 2 by 2 matrix. This is a 2 by 2 matrix, and then we can simplify that like this. The summation can be written as on inner product, like something of vector or matrix transpose on the same matrix will give you the summation over the column. Okay, so we have this. Therefore, so you may write this as like, by the way, for the same reason, um, because like anyhow, 1 over sigma squared does not matter in the minimization problem. Likewise, the same idea holds for 1 over n. So we are going to ignore that, right? So just uh, like we dropped sigma squared from the weighting matrix, we can drop n too. So we are going to use this weighting matrix, okay? And because this weighting matrix does not depend on any unknown, V is all observed variables, so you can just calculate it without estimating any preliminary estimator. Without any preliminary estimation, you can calculate the optimal weighting matrix and then proceed to the main estimator. Okay, so that is how we are going to do it. And in part C, let's go to part C. You know, so and let me finish the GMM estimation. Like the GMM criterion function will be is like this, right? I'm going to call this Q. Sorry about that. So let's call this Q criterion function Q, and it is defined like this. And like and remember, and here using the matrix notation, we defined the sample average of G based on this. So I will copy it. So this is the definition of moment, sample moment, and then using the matrix notation, we can rewrite this as like this, right? The order of beta and x does not matter because anyhow beta is scalar, so you may put it in front or in the back, not a big problem. So then think about the dimension. We have to transpose here, right? So the summation, like, so V is n by 2, and Y is n by 1, and X is n by 1. So you may write it this way, right? So the criterion function can be written as like, by the way, as you know, it is like it's transposed here. So I will change the order, not a big problem, by V. So uh, so this much G hat prime is like this, and times W hat is this, the copy, and then the second G will be here, and I will put 1 over n here. But again, it does not matter. Like minimization does not change even if you have it or not. 1 over n squared does not matter. So like you can delete that, does not matter in our analysis, or you can just multiply n squared because multiplying a positive number does not change the minimization problem. So you have this. And what I want you to show you here is this middle part is projection matrix, right? I believe you have learned this somewhere, like in Econometrics 1, I believe. So we are going to rewrite this part as P, say simply V, okay? So this is what we have, and then you can just go, you can expand. So the first term and second term will be 2 beta PV plus beta squared this one, okay? And again, the first term does not depend on beta. Thus, so this additive constant does not affect the minimization problem, right? Because like plus something does not change the minimum in beta, right? Uh, and uh, and secondly, the vector v includes x as an element. So projection of x onto v is simply x itself, right? Because you are going to explain x using v, then v already includes x, so you can, that's just perfect explanation. you already have all the information of X in V. So your explanation will be X itself. So that is written as uh, PV X is X, right? So this is a property of projection matrix. Projection matrix always satisfies this. Like projection onto the same vector is the same vector. And then and also V is idempotent. Projection matrix is idempotent. So PV is, you may rewrite PV as PV times PV prime, idempotent and symmetric. So in the last term, that means the last term will become the last term becomes like, rewrite last term like this, PVX projection of X. Let me, and PV transpose. This, you may just put additional PV because it's the same as, it is symmetric and idempotent. So we already have seen this here, right? And then you may rewrite this as PV one thing and the same thing again. Excuse me, you do not need to put transpose here. Transpose here, right? So like this, and by the property of projection matrix, you get this, okay? In the end, like combining all the things, the criterion function like I will ignore the constant like this, it is just a constant. You are going to get simple, much simpler form, right? Here, in the end, PV does not matter. V disappears, and its minimization is from which you can find the first order condition would be like this. I believe it should be easy. Just differentiate this and equate to 0. Then you are going to get this. That means in the end, this is a familiar form. It is an OLS estimator. So remember, our starting point was we had exogenous, totally okay regressor, but we wanted to use extra instrument. If the extra instrument helps your estimation, then it will be good to have another exogenous variable, excluded instrument. But in the end, like here, even if you use GMM estimation with the standard like optimal weighting matrix, but in the end, still in the end, it's just same as OLS. So conclusion, when you believe your regressor is exogenous, OLS is the best. GMM or any like two-stage least squares does not help. Okay, thank you for watching. I hope this helps. All right, I hope this saves your time. Okay, and see you later.